Okay. All right, we are recording. All right. Let's go over the schedule real quick. Next week, we do not have class, but in 2 weeks, tomorrow, you guys have assignment 2B is due. There aren't as many files to change this time, but there's still some work to do. So make sure you get hopping on that sooner than later. Also, we have an exam on the 20th. Assignment 2B is due on the 21st. I was kind of rotten of me to do 2 things in the same week, but sorry about that. We got to squeeze it in. We're getting towards the end here. So we need to make sure we're squeezing all this stuff in. We will go over, you know what? I may push the test one day so we can go over more of the test questions, review for you guys right before the test. So I'm going to push it to the 21st. So both things will be due on the 21st. That'll give you guys an extra day, and we'll go over some of the additional things in class. We'll do a quick review. Are you guys okay with that, or do you want to keep it on the 20th? No one's objecting? All right, I see a bunch of thumbs up. So I would say get working on 2B sooner than later, so you'll hopefully have it done before class on the 20th. All right, so I'll push those dates. Other than that, let's dive right into what I want to cover today. And did I hit share screen? I did not. Let me hit share screen. And then we'll be able to see what Dr. Darren has up his sleeve today. It's craziness. I'm just telling you right now. It's going to be a little crazy. So, all right, this week, this is what we're going to go over. We're going to go over some classes in Project Reactor. We're going to talk about backpressure models. We're going to go over some overflow strategies, and we're going to talk about Flux Operators today. And then if we have time, we'll go over assignment 2B. If not, I will send you guys in the discussion board or up on this assignment later tonight. I'll send you videos of overview of assignment 2B. What we're going to do different today is I'm tired of just lecturing you guys. So you guys, when we get to Flux Operators, we're going to break up into groups. You guys are going to have 10 minutes with some help from ChatGPT or Gemini or Claude or your favorite other Gen AI to come up with a course material for everyone else, and you'll be giving that material. You can assign one person in your team to give that material. You'll have probably 2 to 3 minutes to go over that material, and I will be recording that. So make sure when we get to that part that you can hopefully have a slide or something that you can show, and that we can put into the notes as well. So we'll see how that goes today. Hopefully it'll go all right. But all right, any questions on the agenda for today? We all okay? We got it? All right, let's see how we do today. I may change things a lot. There are 3 classes. We talked about these classes last time. We're going to go over them again today more in depth. Mono, flux, and parallel flux. Real quick, mono. Who can tell me about mono?
It represents a single value or an empty result.
Yep, single value in empty result. Thank you, L. All right, flux. Who can tell me about flux?
0 or many results.
0 or many results. Parallel flux. Anyone?
0 or many results at the same time.
Yeah, 0 or many results at the same time. So we'll take a look at how that works today. Okay, let's first dive into mono real quick. Here's some examples. Remember, mono completes successfully or with a failure. It may or may not emit a single value. So there's really, it's almost like 3 states here, right? Empty, failure, or a single value coming out. It's very similar to completable futures. As you guys have remember those completable futures, in other languages, they're called promises that get resolved. It's the same concept. It could, even that value could be an array. It could be a list. It could be, but it's one value coming back. Okay, that's the idea behind it. All right, and you can see mono here. Here's some of the things that we have here. Here's an example, big fraction from callable. It's a mono. I'm going to get one result coming out of this thing in the end. Okay, we can represent, and I want you guys to get used to these. They're called marble diagrams. Get used to these marble diagrams because they'll help us debug. You can even use these when you're drawing things out yourself. But the idea is this, that the timeline is this line that goes across here vertically. So this is through time. And as I go down here, I can see that this mono event is emitted and it passes into this operator right here. And the dotted lines show that it's going to the operator. And the text inside the middle box here, that is the actual operator or the transformation that's going to be formed. And then the yellow cube coming out of the other end, or the yellow circle coming out of the other end, that is the thing that's been emitted out. So that's one value, okay? So you're going to see this a lot. Here's the one value, the orange one coming out. The other thing you're going to see is this vertical line here means that that is now done. It's completed successfully. So on the emitter up here, I emit and I'm done. So that's what that means. Here on the bottom where I see the X is it terminated, right? Abnormally terminated. So the bar terminates successful, the X abnormally terminated. This is just a nomenclature that we're going to use, and you're going to see that time and time again. Okay. Any questions on that? This is a representation of a mono operator here, or a mono, not operator, a mono emitter, I guess is the right word for it. Okay. All right. This is where there are several operators that can be used in mono. And we're going to talk about a lot of these operators in more depth a little bit later, but there's creation or factory method operators. There's transforming operators. There's filter or action type operators. There's concurrency and schedulers. There's combining, suppression operators, blocking. There's a whole bunch of different operators. We're going to go over some of them. And then you guys, as small teams, are going to come up with a list of operators and what they do. That's what we're going to cover today. All right, let's talk about flux. So as we mentioned before, a flux can emit an infinite number of events from 0 to infinity, and it may complete successfully or with a failure. Do you guys remember how I know if a flux is completed? If I'm on the other side, if I'm on the subscriber side, how do I know that a flux completed? Any clues?
On complete method?
Yeah, that's right. An on complete message. I get it. Hey, that's done. That flux completed. This is very, very important, right? To know that, hey, that flux is finished. Unless it's a flux that it just stays open all the time. It may be that I'm just capturing mouse events, maybe. And I'm capturing mouse events forever until someone shuts the machine off or whatever the case may be. Or maybe I'm gathering weather from a weather sensor out in the ocean or something. That's going to keep going forever, I hope. Right? So I may have a flux that never gets a non-complete. Okay. This is very similar to the stream stuff that we were using before, especially the async streams. In fact, if you remember last week, we talked about reactor project being in the same category as async streams and completable futures, a combination of the two. And really, that's where this comes from. Okay, here's some operators of that flux. You can see there's a create operator, a take, flat map, collection list, another flat map, and this multiple events can be passed through here. Okay, so Flux and Mono actually supports back pressure too, kind of, because I'm only sending one event. So, is there any problem with sending one event for back pressure? Do you guys remember what back pressure is?
Like how fast the data procedures are sending more data that can handle.
You're on the right track, El.
It's when back pressure is when there's a lot of delay that is left over from like previous calls. So
Correct. You guys are both on the right track. It's when a
So-
subscriber can't keep up with the publisher,
yes.
right? So I'm sending tons of messages and the subscriber just can't keep up with how many messages are coming from the publisher. And that backs things up, right? And that's that concept of back pressure. So you're both right in what you were saying there. I want a little bit more in that there's several different strategies around what I do with back pressure, which we're going to talk about. One of the strategies with Flux is the subscriber can indicate to the publisher how many events I'm going to deal with, how many I'm going to consume. So in this case here, the subscriber is saying, give me 3. I get my 3 and I'm done. Even though the Flux may continue forward, that publisher may keep publishing, the subscriber says, oh, I'm only taking 3. So this is a natural way of coordinating that back pressure. So that's one technique of doing it, where the subscriber is saying, give me 3. When it has those 3 done, it could actually request for more. Oh, give me another 3. And then the question is, does it start where those pink marbles are, or does it start somewhere else down the queue? And we'll talk about that here in a second. But you guys absolutely need to know what back pressure is. Okay. Any questions on back pressure? You got it? No questions? All right, take that. All right. Here's an example of the marble diagram with this, right? As you can see, multiple events coming through that operator, and I can easily see that they're emitted by the publisher, they go through the operator, and they come out. On the third event coming in, or the third event in the subscriber, what happens there? What's that X mean?
There was a failure.
There was a failure of some kind, right? As you notice at the top, the publisher still is publishing through the operator until it finally gets to the end. But on the third one, I had an issue, right? An exception of some sort. I had a failure. Now, can I throw an exception in the publisher and it be caught in the subscriber like I traditionally use it? Like if I'm doing traditional programming, can I throw an exception in the publisher and it be caught in the subscriber using traditional exceptions in Java? Is that possible? A little bit of a trick question. What do you guys think? And explain why you think what you think.
Can you repeat the question? I'm just trying to
Yeah, so let's say in the top that I have an exception, and the top is the publisher, and I have an error. So I throw an exception. I type in throw exception in my code. Does that exception, is that consumed by the subscriber or not?
My guess is no, because it's going to be isolated to where the publisher tries to emit an event, and then any errors that happen to get thrown from the publisher will be caught in whatever service is monitoring it.
You're actually correct, right? Remember, exceptions are in the same process space, not across process spaces. Remember, with the publisher and the subscriber, they are passing things via messages. Now, what happens under the covers is with Flux, I can actually throw an exception. It gets converted into a message and then comes across as an error message into the subscriber. So, and that's, you have to set it up that way, but it can work that way. So the answer is, I'm not really catching the exception. I'm catching an error message on the subscriber. Okay, so kind of a trick question, but I want to make sure you guys understand the difference. You're in different process spaces. This is really important to understand, especially when you're doing the programming here. I'm passing things via messages, not via memory. Okay, any questions on that? You guys got that? No questions? All right, we'll keep going then. All right. All right, with the Flux, there's a wide range of operators in here as well. And this is something you guys are going to work on as a group today, is going through the Flux operators. But as we already saw a little bit, I have factory methods, which are like create, transforming operators, action and filter operators, concurrency and scheduler operators, combining terminal. This is what it means to end, like on complete or on error. Suppression operators, where I'm not passing things through, or I can block. So there's lots of different things. We're going to categorize those, and you guys are going to show me what they are today. That's what we're going to work on. Okay, let's go to parallel flux. Okay, so parallel flux is really interesting because it means I can run parallel streams of events happening at the same time. So it provides most of the same, not all of the same as Flux. There's a subset of Flux operators. And the operators can convert, the operators can go between Flux and parallel Flux. And you'll see that here in a minute. But these operators allow me to run multiple streams of events in parallel through these operators as they come through, which is really cool if I'm running multiple streams of data and I have one publisher or a subscriber on the other end. Okay, let's see what this looks like. So here's an example of what it looks like. It's very similar to what we did with Java parallel streams, which we did a little bit of this. But you can see I've got how many parallel fluxes running. I've got 3 running on the top, basically. And they're pumping in. And I can sequentialize them. One of the operators is sequential. And then the subscriber can now get them in some sequential event trace. When would I use something like this? A parallel flux? Any ideas?
Well, I guess I might try it when I was doing ETL processes, and I wanted to change a big stream of these types of things into another stream of those types of things.
Great one, right? ETL. What about user interface? Could I use this for user interface?
Maybe loading images on a website.
Loading images on a website could be used. Yep. Think about mouse events and touchscreen events at the same time. Interesting, right? Those are 2 different event channels, all in a parallel flux coming in. Right? Imagery. So there's lots of places where I can use the parallel flux. Okay. All right. let's talk about back pressure models real quick. We talked a little bit about back pressure. Again, who wants to describe back pressure? You guys are going to know this like the back of your hand. Who's going to describe back pressure again for me? I'll call on someone, don't worry. Let's pick on Ronald. Back pressure. Can you describe back pressure?
Yeah, it's a built-in control flow mechanism. It has to do with the subscribe pub sub model. Let me think about this.
When do I have back pressure? At what cases does back pressure occur?
When the subscriber is overwhelmed.
Absolutely, you hit it right. If you said back pressure is when a subscriber is overwhelmed by too many events from a publisher, you get 100% on the test. There's the answer right there.
Noted.
So perfect, right? So that's what back pressure is, right? I can overwhelm the subscriber with events coming out of the publisher. We don't normally see back pressure problems when we do traditional client server. Why? Because the back pressure's on, there's no back pressure because I'm waiting for a return result. So the publisher here on the left isn't going to send any more information until I get a result back. So this is traditional client server. When we do asynchronous programming like we're doing right now, where I just fire and forget, I can build up that back pressure pretty quick, especially if the client can't consume. Client is the same as subscriber. The client can't consume the data fast enough, and the publisher is just sending data like crazy. All right. So we don't have back pressure problems with traditional client server systems. Doesn't exist. Or request response interactions. What's the downside in doing this though? Then why don't we just use client server? Why are we going async?
Maybe to support some sort of bulk action, such as like a huge email chain that needs to get that out.
Sure. Yeah, that's a good one. What else? Anyone? Asynchronous architectures tend to be less coupled. With this client server, I have coupling that exists inherently. I'm waiting for a result. I am blocked until I get that result. So that's a runtime coupling that happens. Okay, so asynchronous, I send and process something else. I can continue to work. Where this, I'm blocked. So you create a runtime coupling, which tends to be bad, but the programming models for async are much more complex, and you have problems like back pressure. So you got to pay attention. All right, so we've already kind of described it, but here's a diagram, good diagram to know if you are still having a hard time understanding. Publisher can send 10,000 events per second to the subscriber, which can only then, send things to a GUI at 7.5 events per second. I have written things like this, and it's a mess, right? Because the subscriber becomes overwhelmed, can't keep up with all the events, and it causes a back pressure problem. So here are the 3 different strategies to handle back pressure. Right, and we're going to go over each one of them, right? One is controlling, buffering, and dropping. Those are the different ones, and we'll talk about each one of them here. Okay, you should know what these are. These will be on the test. Controlling, buffering, and dropping. You should know what the back pressure models are and what they do. So let's take a look at controlling first. Okay, so controlling says, I'm going to tell the publisher that you can only produce events at the same rate the subscriber can handle. In this case, 7.5 kilo events per second. So instead of the 10 kilo events per second, I've throttled it, and that's controlling. Okay, I've throttled the publisher. Now this works really well if I have a one-to-one relationship between publisher and subscriber. If I don't, then this could be very difficult, right? Because am I going to have different event streams for different relationships between publishers and subscribers? And now it becomes extremely complex on the controlling side. There also may be physically no way to do it. For example, if the publisher is a cybersecurity detection system, I don't want to slow that beast down, right? Because I may actually miss some cyber events that are happening. So so controlling doesn't work for everything, but it does work for some things. Okay, it is one strategy. Okay, any questions on controlling? You guys get controlling?
My only question was about the red text. Like, why wouldn't it always be possible? That would be my question.
Because it may be that I have a publisher that's talking to multiple subscribers, for example.
Okay.
Right. And if each subscriber can handle a different number of events per second, which one do I do? Do I choose the lowest one? Now I've slowed everyone down.
Yeah.
Right. Or it could be that they're so decoupled that the publisher and subscriber don't even know who each other really are. I'm just using a message bus and they don't know.
Yeah. Okay. That makes sense.
Those
The
are
multiple subscriber. Yep.
Okay. On the buffering side, buffering is what's typically used with message buses like Kafka. I'm sure you guys have heard of Kafka. Kafka uses something called Kafka logs. That's basically buffering. So what I'm doing with buffering is I'm actually storing the events in memory or on a hard drive somewhere if I want them persistent. The subscriber there is storing all the stuff and then it's pulling things off the buffer. And it's first in, is it LIFO? Yeah, it's first in, first out. So it's a queue, right? So it's very simple, right? It's just passes through. So the buffering itself can handle the events that the subscriber goes. But if this is a long-term relationship between the publisher and subscriber, I could eventually fill up those buffers so that I actually run out of memory. And if I'm doing it persistently, you can fill up, and this has happened a lot. I've seen it happen lots of times. You can actually fill up a whole file system with persistent message events. Now, some strategies that are used to do that is a combination of buffering and dropping. Dropping is where I actually drop events off, right? I say, yeah, I don't care about those events. They're too old, or I haven't gotten to them yet, and I drop them off, right? So that's one of the downsides. Another downside to buffering is if I have a long delay, if I want more of a real-time system, and the publisher can publish at 10,000 events per second, the subscriber can only handle 7.5 events per second, and I'm using buffering, I could be delayed quite a bit as my time goes further and further along. I get this time shift that starts to impact a lot of things. So buffering could be bad too, because the subscriber is not getting things in real time anymore. So if it's a time sensitive one, buffering could be an issue that you got to pay attention to. Okay. Does that make sense on buffering? Buffering actually is one of the more popular ones that are out there that are used in most message buses today. They use buffering. Okay. The last one is an interesting one as well. And this strategy says, I'm just going to drop events. If the subscriber can't keep up, I'm going to drop I'm going to drop those events that I can't keep up with so that I'm always trying to get the most real-time information as possible. So if the subscriber can't keep up, it'll just drop the event and then take the next one off the queue as soon as it comes in. Right. So in this case, I could be dropping 2.5 kilo events per second, which that may not be a problem. It could be, though, if the data is really critical. I don't really want to be dropping events. So can you think of any or any use cases where backpressure modeling with dropping would be a good strategy? Anyone? When would I use something like?
I was just thinking of when people use like something like weather sensors or something. If they're just trying to, you said real-time info is probably the best thing for this. So if you want to just keep an active feed of data coming through, it's better to drop the things that are delayed, if that makes any sense.
Yeah, absolutely. I do a lot of work with the military, and they don't mind dropping events, right? They do mind some events being dropped, but consider this: a submarine goes down for 2 weeks, and it comes up, and it's the subscriber, and it subscribes, and it wakes up and it says, okay, give me the events I've missed for the last 2 weeks. How long would it take to get all those events? It could take a long time, depending on the bandwidth. Now consider the bandwidth is 600 or 900 baud. And for you guys that don't know what baud is, it's really slow. Right? So they drop a lot of events. They're saying those events don't matter, they're too old. So there's a real-time example. Right? I need the latest information. I don't care about old stuff. So weather, in any machinery like control systems, things like that would use that dropping mechanism. Now, are you always stuck with one back pressure model for your whole system? The answer is no. In fact, many times you will see buffering and dropping used together, where I've got one data stream or one relationship between a publisher and subscriber that I'm using dropping, I want real time, and the other one may be a buffering, where I want maybe historical data. Right. So you can see this being used in combinations. Okay, those are the strategies. Now let's talk about reality here. Let's talk about with Flux, right? With Flux on this one, this example here, what kind of back pressure strategy am I using from this diagram that you can see? What would this be called? What back pressure strategy?
Controlling?
Controlling, absolutely controlling, right? I'm saying, give me 3. I get 3. I'm done. Okay. So if you see that on a test, that is controlling. Flux back pressure controlling strategy. Okay. And this is exactly how it works, right? When I do an on subscribe, I can say, hey, I am going to request a certain number of events coming through, and that's it. That's all I'm going to get when I do the subscription. So that's exactly what this strategy is. Right? A very useful strategy in certain things where I need certain values or certain number of values in order to maybe do an average or do some statistical analysis. I don't need everything. Just give me the last bit. Or maybe I'm writing a historical collector that's collecting data in chunks. and I don't want to lose any of the data, so I'm going to collect it in chunks of, I don't know, maybe 100, and I'm going to run a analysis on that data and then store it and then grab the next 100. I could do that. That would be interesting. Lots of different things I can do. Okay. Let's talk about overflow strategies, right? And this is when I overflow. What do I do? There are, and they follow very much what we've talked about before. Remember, we've got controlling, buffering, and drop. So what do you see here? I see buffer as an overflow strategy for Flux. I see drop, where I'm going to drop incoming signals if the downstream is not ready. I have error. It's a signal of an illegal state exception when the downstream can't keep up. So when my subscriber and downstream are the same thing here, when it can't keep up, I throw an illegal state exception. And what I'm basically saying is I can't keep up anymore, right? There's ignore, which says I'm going to completely ignore any back pressure requests. And then latest, which says just give me the latest signal that's from the publisher. So these are different things that you can use in Flux. And we'll show how they're used here in a little bit. You guys are going to show me, actually. Okay, here's an example here, right? So I've added a listener. I got multi-threaded source. I'm producing a bunch of stuff out there. I can see when I'm all done, I remove the listener. I've got subscribe, I've got request, and I've got a cancel here. So you can see how I'm getting stuff and I'm pushing it down into the results coming out. Remember, when I'm creating a flux, I can create that flux with a specific strategy. In this case, I'm saying, give me the latest. So whatever's already been on there, I'm just going to get the latest off of that, from that producer. I don't care about what was there before. So there's my strategy right there. I do a create, give me the latest, and I got the latest, and I just keep going from there. So this is what, this one here is a little bit different. I've got Flux create. And if you notice, what am I doing on this one that's a little bit different? I'm creating this flux to say, if I can't keep up, I have my overflow strategy error. This is what I need to do. Okay, create is showing me my strategy here for error. I'm going to grab all the errors. I'm going to drop, and when I get that error, I do a flat map. And then I'm going to subscribe to the blocking subscriber here. Tie everything together. Okay. All right, let's get that. I already described that. Throw exception when events can't be processed. All right. If I just call create without the latest, that create is going to use buffer strategy by default. This is important to understand this. Buffer is the default, probably because it's the most flexible of the ones out there and the most popular that are out there. So if I call create, I get a buffer strategy. All right. Here is a back pressure drop strategy that I can use. Remember, what does drop do? If I use on back pressure drop, what's it
ignores the message.
Yeah, it ignores any messages that I can't keep up with. Right? So they'll come in and they just get dropped until I can actually consume again. And then here's latest again. Just give me the latest. like drop strat, but it keeps the last emitted item. And this is, I'm hurrying through because I want you guys to do your project here. And then this one here is my buffer size that I have here, and I'm telling it to drop the oldest ones that I want a buffer size of 16, and the overflow strategy is drop the old ones. So there's lots of different options here for me to control my back pressure strategies. Okay, now for the big project today. I've got 5 different flux operators, or 5 different categories of flux operators. And these are them. And I think there's a way for me to push this into all the rooms. I'm going to divide you guys up into rooms. And this is what I want you to do with and they're numbered 1, 2, 3, 4, 5, top to bottom. So whatever room you're in, you're going to take a look at these. What I want you to do for each one of these is I want you to give a description of all the operators that fit in that category. And the name in the description should be the name, the parameters, any configuration values, and when to use those operators. And then I want you to give an example using 3 or 4 of those operators. You can give multiple examples if you want, right? In code. So I want this in code, right? The top part, I want a description, and the bottom part, I want some code for everyone to look at. All right. So quick question from you guys. Do you know what I'm asking you to do? Everyone know? You're going to be in teams of 2. Right? Any questions on what I'm asking you guys to do? I suggest using ChatGPT to help you out. You're going to have 10 minutes to come up with something. You can put it in a slide or in a Word doc, whatever you want. But you're going to have to present it. One or both of you will present it and what you found in each category. How many operators you found, and description. These are the descriptions, and there's the categories. Okay, any questions?
So you're saying we're supposed to, based on our room, we pick that specific operator?
Based on your room, you'll pick that specific operator. Starting at the top is 1, and the bottom is 5.
Okay.
Now, there's more than one operator in there. And my suggestion is using ChatGPT or Gemini or something, prompt it and say, I need flux operators that are method and creation operators. Gimme. And see what it gives you. Make sure that they are Java flux operators. Remember what we're talking about, right? Make sure that you're prompting sufficiently. Okay, does that make sense to everyone? No questions on that. We all got it? All right, I am going to